welcome from my side to the, I think, last presentation of this slot. I'm very happy to present our paper, and I hope I can excite you to have a closer look into our paper as well. First of all, I'd like to introduce our team, our research project, and of course myself as well. My name is Gerrit Placzek. I'm a PhD candidate at the Institute for Construction Engineering and Management at Technical University in Braunschweig. Together with our project leaders and well as co-authors, we participate in a DFG-funded research project called AMC. It's Additive Manufacturing and Construction, and we have the challenge of a large scale. While other project teams are focusing on computational modeling or process control of materials, our team CO6 focuses on design and construction, and especially on the integration of additive manufacturing and construction processes. Okay, let's start with a short motivation. The construction industry is faced with several problems, such as one-off production, a low digitalization. We have a huge impact on the climate change, and to be honest, we have especially a poor productivity. And what usually is done if we are faced with some problems in the construction industry, we take a closer look at other industries that might be ahead of us, for example, the automotive industry. Lean production is applied in the automotive industry and aims to produce goods solely in response to demand rather than produced in stock. It can be traced back to the production principles of Japanese car manufacturer Toyota. But the problem is currently lean production is applied within the construction industry in order to restructure manual construction processes. However, advances in the field of additive manufacturing with concrete are opening up new construction opportunities and production principles. In particular, Shotcrete 3D printing as one method of additive manufacturing has the potential to lead to significant improvements in productivity and also to a sustainable production process. And what happens when we combine lean production and additive manufacturing is quite interesting. On the left side, we have the 5 principles of lean production. On the right side, we match them to additive manufacturing. And let's go through 3 of them because we are only limited in time today. Value is only what the customer is willing to pay for. Changeover times of machines or formwork, for example, and the resulting manual effort are currently unavoidable to produce different component types. But those are non-value adding processes. By using AM, a new level of form flexibility and more opportunities to produce different parts is gained since formwork is no longer necessary, resulting in a customized or even individualized components based on what the customer is willing to pay for. Secondly, not only material, but also information was provided in the correct order. AM enables both due to direct transformation of the virtual designed and physical object, making it possible to create a continuous production flow. Last but not least, AM is a fully digitized design to construction workflow where the actual production tasks are reduced to printing. This allows us to produce components on demand with a high level of flexibility in form and production, where we eliminate long inventory times and in consequence costs, such as it's currently done in prefabrication. Let us now have a closer look on Shotcrete 3D printing as some sort of case study for us and why we need lean production for additive manufacturing. Shotcrete 3D printing has been developed at the Digital Building Fabrication Laboratory at the TU Braunschweig. It is characterized by the production of solid wall components with high printing speed and high productivity. Unlike other additive manufacturing methods, concrete components are built up layer by layer, but with a controlled addition of compressed air. Shotcrete 3D printing consists out of a combination of additive and subtractive manufacturing tasks, as we can see on the right side. There we have, for example, additive tasks such as core printing and the second layer printing, but we also have subtractive tasks like edge milling, rough surface, or final finishing. During these tasks, predicting the behavior of material is quite a challenge. Parameters like nozzle distance or spray angle or printing speed have a major influence on the printing quality. Therefore, a component improvement process consisting out of multiple interlocking tasks, such as I named them, edge milling or surface finishing and quality inspection, are critical in most cases. Oops, sorry, I'll go too quick. And if we have a look at all those points I just addressed, as a result, we need an overall approach to optimize Shotcrete 3D printing. And therefore, I'd like to present the core aspects of our lean-based production approach. Combining the two lean principles, map the value stream, and establishing a pull production leads to an on-demand production. Since Shotcrete 3D printing components can be produced without any long time because we do not have any formwork, for example, and we can directly transform material into a final product, a pull production gets within reach for construction industry. For example, the construction site as a customer could communicate the demand concerning individually designed components and create an on-demand production where deviations are eliminated. On the right side, value stream mapping is shown. It is a lean production method often used to analyze the production processes. But in the context of Shotcrete 3D printing, this technique is confronted with various adoptions. Since Shotcrete 3D printing is a method where no geometrical standardized components are produced in series, but rather serialized individual production parts, the design to construction workflow is nearly the same, but production times vary in each case and every time for different components. Due to the lack of formwork and hence lack of precision of AM processes, bidirectional information workflows provide the framework to ensure component quality. Bidirectional workflow represents a combination of pursuing perfection and also creating continuous flow. In this workflow, a fabrication model, as you can see on the right side, is created from the as-planned designed model, which includes the path planning along fabrication parameters. After the transition to fabrication and actual execution of the process is validated by a data acquisition and subsequent analysis. Depending on the measured geometry of the actual produced components and previously produced components, the process parameters can be adjusted after each validation step. With the help of such short cycles of quality control, the desired component quality can be achieved. In order to control various tasks of the manufacturing process, quality control must also take place, which leads us to the third part of our approach. For example, we must ensure that, the core is printed accurately. If we have some reinforcement, it must be placed correctly. The edges should be cut precisely. And also we want to have a surface that has the right or the high quality. And what is being checked here is defined by the customer, for example, the owner or the engineer, and therefore we pursue perfection within quality control. The subsequent graph is a layer-wise quality control. After every layer, the printed object would be captured, then compared to the designed model, and then another layer would be printed based on the results of quality control from the previous layers. By applying lean principles to production quality control processes, a higher component quality is expected, as well as a significant reduction in waste during production and hence a higher productivity. We have seen that bidirectional information flow provides the framework for the integration of additive manufacturing in construction and remains a necessary requirement for our lean-based production approach, as well as tolerance checking. A holistic process understanding as part of lean methods ensures that an on-demand production is possible and the project goals or the defined value can be fulfilled more efficiently compared to the current situation. We also know that there are still some challenges, especially because of naturally occurring processes, but our approach is currently, and we know that our approach is currently more a framework while we need to continue our research. We're quite sure that the integration of AM will finally lead to a new way of construction. Thank you very much for your attention, and I'm happy to hear you.